Thank you very much, Yifeng, for the introduction, and I would like to thank the organizers for giving me the opportunity to speak remotely in this workshop, my first Zoom talk ever. I will speak about scaling limits and stochastic homogenization. That's a very recent joint work with Cardaliaguet and Souganidis. And to motivate it, let's go back to the remarkable paper from what is now the previous century by Funaki and Hamilton-Jacobi, a model for stochastic mean curvature flow, a very much regularized model, but stochastic. So what is happening here? Phi of t is the height of a surface over a basis plane. So the surface moving by mean curvature is a graph given by phi of x at time t, and x is discrete. It lives in a subset of the integers. Now it moves driven by a potential. So we see here essentially the sum over v prime of the discrete gradients is something like a discrete divergence of a nonlinear function of the discrete gradients, but there is a stochastic input for each height phi t of x, which are independent Brownian motions. Now, as you all know, mean curvature flow is a very degenerate problem, while that here is regularized in the sense that v prime is the derivative of a strictly convex symmetric potential v. Think of v of x being the square. You get here the discrete Laplacian, and you get a discrete version of the stochastic heat equation. Now I plotted here two realizations, and you see this is completely random. But now we can look at it on a large scale, do a scaling limit, and as heat equation or motion by mean curvature are invariant under diffusive rescaling, so rescaling time with the square of the rescaling applied to the space, it's a natural choice of rescaling here. So Funaki-Spohn did that, and the rescaled heights are now called phi epsilon. Time is accelerated by epsilon to the -2, and space is scaled down by epsilon. So we approximate now a function on the continuum by a function which is piecewise constant on little cubes of side length epsilon. However, as mean curvature of a graph is actually something that happens in the d+1 dimensional space, we have also to scale the heights themselves by epsilon. And then they showed that this converges to the solution of a deterministic PDE, which is of the same structure as the ODE, just with an effective potential here. Capital D is the derivative. To distinguish it from the continuous derivative, to distinguish it from the discrete gradient we had before. So this is simply a nonlinear divergence from deterministic PDE. And this passing from a stochastic interacting system of very many stochastic processes to a PDE is called the hydrodynamic limit, historically motivated by the fact that one wanted to derive basically from Newton's laws, many little balls banging into each other, the Navier-Stokes equations. It has nothing to do in this case here with real hydrodynamics. It's just a name. And if we compute that on the diffusive scaling here, n is equal to 100, so epsilon is 0.01, we see that this looks really very much like a sine damped out by the heat equation. So in the paper, the technical key was, and basically also a question of independent interest, was invariant measures for this high-dimensional stochastic process. So the idea is we define things on a finite lattice and let a finite subset of the lattice, lambda, and that this tends to settle D. So we have in the limit an extremely high-dimensional stochastic process with nonlinear interactions between all the phi t of x. So and this process, of course, on a finite domain has an invariant measure, and it's easy to see that it can be written in this type, in this way, where we sum over the potential now, V prime was the driver here, V is the potential, and integrate against all the possible positions, heights of phi. And then we normalize that by 1/z to make it a probability measure. Now we see also if we really take for V here the square, we have here simply independent Gaussians. Now one can make sense of that in the limits finite domain lambda going to all of z to the d. These finite dimensional measures here have some kind of limit points, and these limit points are called DLR states, named after the Bruschi, Lanford, and Riel. If the conditional expectation of this measure on the whole space conditioned on a finite cube lambda with suitable boundary conditions looks exactly like here. And Funaki and Spohn showed, and that was a very important result independently of the limit result, that for each tilt of the surface, there exists a unique such DLR state mu of p. Now, what does tilt mean? I can replace my potential v of y by v of y plus p, and then put periodic boundary conditions. So instead of looking at a surface with a tilt, I can look at a flat surface that kind of tilt the potential. So for each tilt P, there is a unique DLR state. And now we're kind of getting closer to the connection for homogenization. There exists something for each P, where P is kind of a gradient, a tilt, that reminds us, of course, of correctors. Now, quickly, what is the technique? That's something that goes back to Guo, Papanikolaou, and Varadhan for another system of interacting diffusion processes, local equilibrium states. So we have a macroscopic quantity, kind of the gradient of our limit PDE, which on the microscopic scale varies very slowly because it varies of order 1 on the macroscopic scale. Now, if you blow up and go to the micro scale, then there the process, we start with a process with initial data which are prepared such that they in law measured by relative entropy close to one of these invariant measures which are unique up to tilt with the tilt P of x, which is exactly our gradient of h. And that is actually preserved in time. One can show that by decays for the relative entropy, and allows us to replace nonlinearities by the expectation under this measure. So similar in, if you look at typical formulas for, which we'll see also later, for effective homogenized nonlinearities, that is kind of an integral with respect to something that involves the corrector. The same here, the expectation under something which plays here the role of a corrector. And of course, it's crucial that this mu p is stationary and ergodic in order to get something deterministic on the macro scale. For more details, I refer to the monograph by Kipnis and Landim. Just one important fact that we will come across later in a homogenization setting. For 1 and 2 dimensions, there is no invariant measure for the fields itself, only for their gradients. Now, think of you have simply 1 dimension, lambda are simply the numbers from 0 to n, and you put on each integer an independent Gaussian, then you would expect fluctuations of order square root of n. So obviously, if you send this to infinity, there is no tightness, so you can't expect in these low dimensions that the fields phi themselves exist. But fortunately, for getting this equation here, because on the right-hand side, you sort of plug in here only the gradient, that is not an issue, and we will see that later again appearing in a more PDE context. So given this paper from the 90s of the last century, and given the tremendous progress in stochastic homogenization that has been made in the meanwhile, the question arises, can we do something similar for stochastic PDEs instead of interacting diffusions, which here in this case are just sort of a discretized PDE? And can we use homogenization techniques instead of the techniques described here in this slide and used by Funaki and Spohn in 1999? We took the following SPDE as a kind of a starting point or toy model that has a lot of features of the Funaki-Spohn model. What we have here additive noise, so there is no existence and regularity issues here. We want to model an input of the noise which is spatially very short correlated. Now, there are several ways to do that. We chose to do it by choosing here a cut-off function A, which is smooth and has compact support. So think of the space chopped up in the supports of the translates of A, and on each of the supports acts an independent Brownian motion. And then we have here, like Funaki and Spohn, a nonlinear divergence form equation. And in order for the regularity requirements and non-degeneracy requirements can be relaxed, but in order to really have the companion result of Funaki and Spohn, we basically need similar assumptions to there, so some strict monotonicity of that operator. So, and we add in addition here an additional random dependence. So that's now a random monotone operator, which is a stationary ergodic in space-time, and in space, we have the action of Z to the D, in time, we have the action of R, and that comes simply from the fact because we chose to model our short correlations here in this way. So the coefficients themselves, of course, are stationary only with respect to Z to the D. That is an artifact of the way how we chose to model the noise in this example. And it will turn out that in the way we are going to do it, that additional randomness of the coefficients, which is assumed to be independent of the Brownian motions, is no additional complication at all. So this can be done in one go. That is now a PDE analog to the Funaki-Spohn model, but in fact it's different. So, I mean, our result doesn't apply to their setting, and their setting doesn't apply to our result. Why? Well, Funaki-Spohn looks like a numerical discretization of such a PDE, but there's the issue of scales. If I discretize this operator here by finite differences and make the scale of the discretization much, much smaller than the support of A, then I have a discrete model that in the limit will behave like our model here. If however, I make a discretization on the same scale as the support of A, then I have something that is more like the Funaki-Spohn model. We will have a similar result, but the effective homogenized equation will be different because now the two scales really interact, which creates new effects. So qualitatively similar, but a different model. Now, our aim here is to use homogenization techniques to show that solutions of this equation in the limit epsilon going to 0 converge to solutions of a non-deterministic nonlinear divergence form equation, where the nonlinearity is an effective nonlinearity that I can compute from A, and the corrector that is informed by the noise both here and by the Brownian motions. Well, there are several other works trying to connect homogenization and stochastic PDEs, limits of stochastic PDEs, but they were in linear situations. There is, of course, the work by Zeitouni, Rissike, and Dunlap, and there is also a work by Haira, Pardue, and Gieditsky, where they go kind of step further and approximate also the Brownian motion by suitably scaled Gaussian random variables discretized in space and time. But these are all linear examples. Here we have still divergence forms, so we can integrate by parts, but non-linear. Let me quickly introduce my take on the difference between homogenization and scaling limits for interacting particle systems, as in the Funaki-Spohn example. In homogenization, there is a law of the microstructure, which is stationary ergodic, but it's fixed, it's given, it's part of the problem. Whereas for interacting particle systems, there is an ergodic structure on the microscale, but it's self-organized by the particle system. So that is not a priori given. And the invariant measure of this, local equilibrium measure, the local equilibrium states, or maybe generally the invariant measure corresponds now into the law of a gradient corrector in a homogenization language. But the difference is that in one case, I kind of plug in the randomness at hand. It's given to me. In the other case, I have to extract it from the stochastic PDE or from the interacting particle system. Now it's time to state for the first time our result. Again, as I mentioned already, that is a collaboration with Pierre Cardaliaguet and Souganidis. So we have the solution of this equation, where for convenience we add a fixed, smooth deterministic macro right-hand side, a monotone nonlinear divergence form operator, and some scaled noise, which is smooth, which fixed epsilon. So we don't have to worry about existence at all. That is additive, noise, smooth, and x, white, and time. But as you see, if epsilon goes to 0, the correlation length vanishes, so sort of that approaches white noise, while simultaneously there is a homogenization limit going on. And the result, due to the averaging of the strongly monotone operator here, will be a deterministic PDE. So it converges almost surely in the expectation in suitably weighted N2 spaces to unique solutions of a nonlinear divergence form equation. And again, we need, for going all the way, that A is strictly monotone, and so will be then the A bar. We are here on the whole space setting. So we set all the problems in the whole space. That's kind of natural in homogenization because there are correctors usually from the whole space on R to the N, which introduces loss of compactness and all the associated complications. But often the macroscopic problem is fixed with boundary conditions or on a cube. Well, you have to make a choice here. I mean, one way to get not having to worry about boundary layers is periodic. Another is to be on the whole space. Each has additional complications. We chose to set it on the whole space as well. So let me briefly outline the strategy of this proof, and that should also explain now more precisely the connection with homogenization. Now we split our solution of the SPDE u epsilon t of x in two functions. One solves, the W solves the deterministic divergence form nonlinear equation, and the other solves a stochastic hit equation. Now here, that I can do in general, and if you do the straightforward computations, you find that the nonlinearity here of the W equation is the old nonlinearity plugged in the gradient of the solution of the stochastic heat equation, and then minus that term again. Now, if my original equation was strictly monotone, I can choose here in the heat equation a small delta times the Laplacian, and I can write my original nonlinearity as a small Laplacian plus something which is still monotone. That's using the non-degeneracy, the strict monotonicity, and then this term goes away, and we immediately see that a new nonlinearity inherits all the nice properties of the old nonlinearity. So in other words, under the same structural assumption as Funaki and Spohn, it is obvious that this new nonlinearity is a new random nonlinearity, however, satisfying the same assumptions as the old one. Now we have here two sources of randomness, but they are independent, so we can simply move to the product space and, in order to simplify notation, from now on write that simply as a new random nonlinearity, A of P, T, X, omega. We also see that for this new random nonlinearity, we only need a gradient of the solutions of this equation, which is good news because it will turn out that, as in the Funaki-Spohn case, in low dimensions, d equals 1 or 2, the fields themselves will not have any limits as we make time big, so we cannot hope to get anything ergodic, any limit, invariant limit measures as time goes to infinity for the fields itself, but only for their gradients. But the gradients, it's all we need to construct our random nonlinearity here, homogenize that equation, and obtain the result. So the tasks are, we have to show that this equation converges to an eternal, stationary, attracting solution if I consider only the gradients, because the gradients is all I need. And then once that is done, we have to homogenize the second equation, a nonlinear divergence from PDE. Here the randomness is ergodic with respect to space and time, and the regularity in time is not very good. It is just Hölder continuous because of the fact that we have here a Brownian motion. So with here the V Brownian stochastic integral. Okay, so we have split up the proof of a scaling limit for stochastic PDE, which is a similar model to an the process of interacting diffusions, into two parts. One kind of nonlinear homogenization part and one stochastic part, where, however, we have a linear equation, the heat equation, and are able to use the Green's function representation. Let's do a look at the first part, the stochastic heat equation. Okay, we want to find eternal solutions of that equation, so solutions that live for time in R, and we want to show that the solution is unique and attracts all other solutions. As a consequence, its law is ergodic in space and time, which is exactly what we need for plugging it into nonlinearity and homogenizing. So how do we do that? There's a standard way to do that. We look at solutions of the equation at initial times minus n squared with initial datum 0 and send n to infinity and hope that the initial datum will be forgotten and this Vn, which started minus n squared at 0, form a Cauchy sequence that converge to an eternal solution. So what do we need for that? We need moment bounds for solutions of that equation, uniform in time. We need a correlation decay. We'll see later why that is important. That we hopefully get from the fact that the Brownian motions are independent that are driving the whole thing. And then we have to show the convergence as n goes to infinity. So 3 steps. Let us start with the first step. Moment bounds. Well, if we look at the second moments of the fields itself, for small times, we have here CT, but we are interested in large times for convergence towards something invariant as time goes to infinity. So let's look at that part. If the dimension is larger or equal to 3, we get here uniform bounds, uniform in time, but not for the dimension 1 and 2. As I mentioned in the Funaki-Spohn case, the fields themselves do not have a suitable invariant measure. They fluctuate too much. However, for the first and second derivatives, this is okay. We get a uniform bound in time. So there is hope to get some tightness as time goes to infinity, to get some invariant measures. But that's not enough because we want something that is stationary in space and time and a solution of the equation. But we see from that already, the limits are general in higher dimensions expected only for the gradients. Oh, and the methods of these moment bounds are simply use the Green's function, the heat kernel representation, and use Ito's formula and try to estimate all terms that occur. Computationally intensive, but there is nothing too tricky about it. Now, in decorrelation, we want to show that the solutions are almost independent at points x and y that are very far away from each other in space. Now we can hope for that because the inputs, the driving noise, are independent Brownian motions, and the heat equation kind of averages as time goes by over larger and larger areas. So the input from very far away should come only through its average, so deterministically, and not create any correlations. Now, technically, how do we do that? We look at solutions VTLR, where we look at a new driving noise, where we have switched off all the noise outside a ball of radius r around a point L. Now, the hope is if r is very big, that at the center of this ball, the effect of having switched off the noise very far away is not felt. And that's indeed the case. Let's say our L is 0, it's everything stationary in space by construction, so that's without loss of generality. Then if r squared divided by t is smaller or equal to 1, so after large times, which is the case of interest here, we have the decorrelation decay like r to the minus d for the gradient. And moreover, this VLR that approximate for big R, our original functions, are of course independent from each other if the distance of the two centers is much bigger than R, because their driving input are completely different independent Brownian motions. So in this way, these VLRs allow us to use that to make a quantitative the fact that our solutions to the original stochastic heat equation are almost independent at points very far away from each other. And that will be important now for the convergence, what we're actually after, the convergence for the solutions for our initial problem starting at times minus n square. We want to show that the gradients are a Cauchy sequence uniformly, locally, so in compact space-time domains. Now the idea is that the difference of two solutions of that equation solve a deterministic heat equation, because the driving term, of course, drops out. The heat kernel is averaging. Essentially, the heat kernel is an average over a domain of square root of t. Now we replace V by VLR and we make an error here, but we can make this error smaller epsilon if we make R very big. And then however, the heat kernel averages over a sum of independent random variables, and that we can control with the Lie law of large numbers. So we can make two errors small and show that this is indeed a Cauchy sequence. And a similar principle we use to show that the solution, which is the limit of the Cauchy sequence, attracts any other solution. Again, the difference of two solutions satisfies a deterministic heat equation. We have some averaging principle for the heat equation. We have your uniform gradient bounds, make the ball bigger, and we see that the difference has to go to 0. So we have shown that there exists the eternal attracting solution of the stochastic heat equation. Its law, therefore, is ergodic and stationary in space and time, space under Z action, time under R action, real numbers. We plug that in our nonlinearity and are reduced to a homogenization problem. So let me sum up what we have done so far, what one could call self-organized ergodicity, how to get from a scaled SPDE to a space-time homogenization problem with stationary ergodic random coefficients. We have this eternal solution. It's an attractor. In lower dimensions, that's only true for the gradient. That's here. Z solves the equation for the gradient. That's why there's a derivative. In higher dimensions for the fields itself. And important consequence, our new nonlinearity, our new random nonlinearity is stationary ergodic. And now, basically, for the second step, we can forget about stochastic heat aggregations. We can forget about Brownian motions. We have to deal only with space-time stationary ergodic homogenization of a nonlinear divergence from parabolic PDE with a strictly monotone operator. So the second part is just about nonlinear divergence form homogenization. And there I should I mention briefly our result first, and then some related work in a moment. Okay, now we forget about the Brownian motion. We have this structure, ut epsilon minus divergence monotone operator, a of du, x over epsilon, t over epsilon square omega equals the right-hand side, strongly monotone, usual regularity assumption, stationary ergodic with respect to steadily d times r action. there exists a corrector for each P, which is normalized to be 0 on the unit cube. Again, we are here through the original choice we made for modeling the analog of Funaki-Spohn in a PDE. We have here set to the D action. So normalizing means centering it on a space-time unit cube, instead centering it simply at 0, 0. But practically, that is the same thing. That is h-1 in time and h1 in space. Now, the bold spaces here mean that, as you will know, that if I have something stationary ergodic, I can lift all differential operators to the probability space using stationary ergodicity and define there the same Sobolev spaces as we're used to on Rn. But to distinguish them, they will be denoted by a boldface letter. Now, this corrector solves in h-1 the corrector equation, as it would be expected for a corrector. And then, of course, it has to have an important property, which is often the most difficult thing to show, and that is sublinearity. And here we need parabolic sublinearity, so time is of order epsilon to the -2, but the thing is only scaled by epsilon and still has to go to 0. So it's in principle a more difficult to show requirement than the standard sublinearity one would expect from stationary or hyperbolically scaled equations. So this is the main result. Then there are some additional complications using the perturbed test function method, to which I go later. And in that setting, to my knowledge, that is a new result, although there are, of course, papers on time-space ergodic homogenization. Now, the second part of the result is homogenization and effective nonlinearity. Well, of course, solutions of that equation converge to a solution of an equation of the same structure with an effective nonlinearity that I can compute as the expectation of my old nonlinearity plugged in the corrector. So a formula as you would expect from stochastic homogenization. Now, some related work for nonlinear divergence form. There are papers quite a while ago from FND, Panov, and Chiang. They do not fit in the generality and regularity settings in which we need it here, which are dictated by the fact that we started from a stochastic SPDE. There is, of course, starting from the works and the monograph of Zhikov, Kostov, and Lemanik, a lot about linear equations. I would like to point out in particular that there is a quantitative approach by Armstrong, Bourdin, and Tumorin, while we are doing here qualitative homogenization. So we are not aiming at error estimates so far, but as far as I know, that quantitative approach is still restricted to the linear situation. And there's a nonlinear works on nonlinear time-space stationary ergodic homogenization by Jessica Lin, Charles Smart, but it's a different type of nonlinearity. So we have kind of, in order to get our scaling limits, we have also a new divergence form, nonlinear divergence form, homogenization result, and existence of corrector result. So what is the strategy for constructing the corrector? Well, you start, as one probably would guess, we have here two problems for solving that equation. So there are two problems why a good student taking a postgraduate PDE course couldn't immediately solve it, and that is the space is not compact, and the equation is maybe a bit nasty, a bit degenerate. So what does one do? We get a priori bounds by adding a lambda times u here. We make it an elliptic equation by adding a lambda, the second derivative of time here. And we restrict it with 0 boundary conditions to a finite cube to get away with, to get rid of the non-compactness. So now that's kind of a textbook problem. Existence is straightforward. And the question is, do we have a good a priori estimates for some quantities, hopefully independent of L? Yes, we do. Then we can let L tend to infinity, extract convergent subsequences, show they converge to a solution of an equation for which we have uniqueness. And in this way, we obtain a solution of a regularized equation on the whole space now, but still with that lambda regularizing it by making it parabolic and making it bounded. Now we need to get estimates uniform in lambda, and now it starts to get a bit tricky because we can't hope to have an estimate in L2 for the solutions uniformly in lambda, because as I've mentioned many times during this talk, in dimension 1 and 2, typically the fields themselves grow too fast. However, we have estimates for derivatives in L2, and we have estimates for the time derivative in h-1. In order now to pass to the limit and show that the limit really solves the corrector equation, the problem is there's a nonlinearity. So you can't simply multiply by a test function, use V convergence. We have to push somehow the nonlinearity through the weak limit procedure. That, of course, uses the monotonicity, but we need also some lemmas on reconstruction of stationary functions from derivatives, which may be of some interest in their own right. In some version, they are kind of standard, but again, they had to be adapted to our setting, which is slightly different, be it only by the choice of set to the D action. So the first such lemma is, there are two lemmas, which I decided here now to put into one to save a bit of space and time. So if we have a vector field, a stationary Gothic vector field, which is the derivative of something, so it's potential, and we have something in a negative stationary Sobolev space, and they satisfy these compatibility conditions, then there exists a function u such that w is the derivative of u in space and phi the derivative of u in time. Now, if you check what these compatibility conditions mean, it is simply that dt by dx is the same as dx by dt. So that is something which from differential geometry, of course, we know, but here it's kind of lifted to the space of stationary fields. Now, the important estimate is the following, and the important fact is the following. If we have addition a vector field psi that satisfies theta minus divergence psi equals 0, then the expectation of w times psi is 0, again, because of set action, set of the action integrated over the unit cube. Now, that is the type of structure we get from our limit procedure for a nonlinear equation. And your nonlinearity converges weakly to some psi, your gradients converge weakly to some potential field W, and your time derivatives converge weakly to something h-1 called theta. That's exactly the structure we get from extracting weakly convergent sequences. And then we can, however, have some additional information which will at the end allow us to identify the nonlinearity as what we actually hope to identify, this psi as the A bar of, as the A of P plus gradient chi. The heuristic for that is, let us consider the following. The W is gradient U, let's plug it in. Psi is theta, and we integrate by parts. So psi is divergence psi is theta, we integrate by parts, we get divergence psi replaced by theta, which however is dtu. Let's replace it here. So that actually is the derivative of 1/2 u squared. Now that's a positive quantity. If this wouldn't be 0, by stationarity and ergodicity of these guys, which are ergodic unlike the u itself, this positive quantity would have to grow linearly, but that's impossible for a positive quantity unless it's 0. That's a kind of heuristic of the proof, and then of course one has to make all this rigorous, which requires a lot of time. But that is one of the ingredients on passing to the limit. A further ingredient is important lemma to show the sublinearity. Now, to show parabolic sublinearity, we first need the usual kind of hyperbolic sublinearity, and then combined with estimates like that, we can use this to show that we actually have parabolic sublinearity. Now, this means the limit, if I divide u by r and average over the cube goes to 0. So that's just the usual sublinearity of something where the gradient in space and time is stationary. Complication here, the time derivative is only in h-1. Additional complication, to integrate along paths, we need kind of ergodicity along lines instead of the total ergodicity. But that is taken care of by a lemma we adapted from Kosigina and Varadan. We had to adapt it because we have this set-to-the action again. And that's, of course, equivalent to saying that this hyperbolically scaled function converges in L2 to 0, almost surely. Now, with these ingredients, we can show we can pass to the limit, show that the limit point satisfies the corrector equation, and we can show that it satisfies parabolic sublinearity. Then we can do the homogenization with the perturbed test function method. And another problem appears, that is that we have, as many times in homogenization, very low regularity in P. And therefore, we can't simply plug in chi of, instead of P gradient of our limit of our test function phi. We need to approximate the gradient by piecewise constant functions. And in this way, then we can finally get the homogenization result. So summing up what we have done so far. Well, the main result is a scaling limit for SPDE by homogenization techniques. You have an SPDE, divergence form, nonlinearity, strictly monotone, random in itself, driven by Brownian motions which are short correlated but smooth in time space and wide in time. They converge almost surely in the expectation to a solution of a deterministic nonlinear divergence form equation with an effective nonlinearity A bar that we can compute using a splitting procedure and construction of a corrector. In order to get there, we needed an independent result on existence of correctors and homogenization for a nonlinear divergence form equation with a space-time stationary ergodic noise scaled parabolically. We showed existence of the correctors and, of course, their parabolic sublinearity. And we have a explicit formula using the corrector for the effective nonlinearity. And morally, this formula is actually very similar to the formula Funaki-Spohn got in their paper. Now, where can we go from there? Here, the paper is on arXiv in case you're interested. But certainly it would be interesting to make more precise the connection with the Funaki-Spohn paper. So basically use our methods for their discrete PDE to show that we obtain the same result with our methods, and also make more precise this crossover in the discretization of our nonlinearity with a finite difference scheme. Then I said mean curvature flow is of course far more degenerate, and mean curvature flow is of course, stochastic mean curvature flow is of course far more complicated. First of all, you should not have here additive noise, but a multiplicative noise of the form square root of 1 plus du square, which however stops it from being a graph almost immediately. But as a step there, we could look at more degenerate operators as von Renesse and Essayer investigated in a paper where we have here basically the operator in one dimension, basically what one would get from mean curvature flow from a graph, so a more degenerate operator, not anymore strictly monotone, but here we put still the additive noise. And adapt our techniques to this case. Well, hopefully we have found a technique to use modern homogenization techniques to a large class of problems. If we want to cover the type of problems that people have considered when looking at scaling limits of interacting particle systems, for for PDE formulation, we would also have to look urgently at multiplicative noise to cover all the cases that have been covered with other methods. So that's definitely a new problem. It creates some complications. One would probably have to show the existence of the ergodic state with via a fixed point principle. Another question would be Allen-Kahn type problems, kind of another regularization of mean curvature flow. And then an interesting problem is, can we have a dynamic Leibowitz-Penrose limit? So what is that? If you have Katz type interactions, so you replace some short range interaction like in the Funaki-Spohn method by some intermediate, some averaging over still less than macroscopically many, but very many particles, a local mean field limit, then you can show things that you otherwise wouldn't be able to show. So this way, Presutti, Di Masio, Landi, and Riolo, and Katsoulakis and Souganidis showed convergence of some Katz type easing models towards motion by mean curvature flow. And the hope is that, as in the static case, that's the Leibowitz-Penrose limit, the situation for a long but finite interacting range is very close to the Katz limit. So can we do something in the graph situation here by doing a kind of graph-type Katz model for mean curvature flow from easing and show that at least in the graph case, this is true, what somehow people haven't been able to show in the general easing model case. So with that, I would like to conclude, and I thank you all for your attention.